called Seafloor Spreading in this video. And to start off, let's discuss some of the things we've already talked about. Now, we've already discussed in previous videos and in class discussion what went wrong with continental drift, and moved around two things. First off, Wegener couldn't really tell you how continents moved. He thought the continents were moving like a snowplow through the ocean crust, which would have caused the ocean crust to crumple. This is not the case. He also missed the mark when he was describing what was actually driving the motions. He said it was the moon, and the moon does not have the force in order to move continents. So before we get into seafloor spreading, let's talk about some alternatives at the time for continental drift. One was expanding Earth theory, and the other was the shrinking Earth theory. So with the shrinking Earth theory, what they were trying to do was explain mountains. How do mountains form? And the thought was that as the Earth cools, like many things, it contracts. When it contracts, it would bring continents closer together, and mountain ranges such as the Himalayan mountains would be formed in these regions. Another competing theory was the expanding Earth theory. So instead of the Earth shrinking, it was actually expanding. And this is why the continent shapes are the way they are. Because before, the continents were all together, and as the Earth expanded, it caused the continents to drift apart. Now, both of these had huge problems. Obviously, the Earth isn't getting any bigger, nor is it getting any smaller. So we have to have something else to help explain how the continents move and what drives them. And that gets into seafloor spreading, which is what this video is over. But before then, let's back it up again and let's talk about what we used to think about the ocean floor. Again, to summarize the stuff we talked about before doing the previous lab, we used to think that the ocean floor was extremely old. They thought that was where you would find the oldest rocks on Earth. We also thought it was going to be extremely flat, basically a giant plain in between the continents, and also unchanging, that nothing geologically speaking was happening down there. Now, we already figured out some of the ways that this is wrong. First off, let's talk about some of the topographical surprises. When we looked at the ocean floor along the Atlantic, we found that it wasn't actually flat. We found, in fact, that there was this very large, in fact, the largest mountain chain in the world, all right, the Mid-Atlantic Ridge, all right, that spans the entire length of the Atlantic Ocean. It actually matches the same shape of the continents. All right, so that was a big surprise. No one was expecting to find the world's largest mountain chain in the middle of the Atlantic Ocean. Another piece of evidence we found that was a surprise were these trenches, all right, along some continental margins, and those continental margins then also had volcanic mountain ranges, in this case the Andes. All right, but these trenches, these deep, deep parts of the ocean, are found also in the Pacific, all right, along the coast of Asia, all right, along Japan. All right. We've got some even in the Caribbean, all right, always associated with some kind of volcanism, which is interesting for later on. So beyond topographical surprises, there were some other things that surprised us when we started really looking at the ocean floor in detail. First off, when we were drilling into the ocean floor to get an idea of their age and compositions and things like that, we found that it was covered in sediments, but those sediment layers are not really uniform. But there was somewhat of a pattern. In fact, as we started drilling these cores, we found that the ocean crust, which is basalt, was covered in layers of sediment that became thicker and thicker the further away we went from the mid-ocean ridges, which again indicates that the age isn't uniform. Didn't all form at the exact same time, because the way these sediments form is basically things rain down or like snow. As little micro fossils die off plankton and the phytoplankton and things like that. It just creates this rain effect, or snow that builds up. And the thicker the layers, the more sediment's there, which implies that it's been around longer. So we have these thicker sedimentary layers away from the mid-ocean ridges, which also ties in with the paleomagnetism. All right, paleomagnetism. What in the world is this? It's basically just the record of Earth's magnetic field over time. The nice thing about the ocean floor being basalt is that it can actually record which way the magnetic field is facing during the time of the formation of that rock. Basalt is an igneous rock. Igneous rocks form when magma or lava is cooling off. And since basaltic magma is so rich in iron, the iron acts like a little compass, and compasses always face north. So when that rock cools and hardens, it actually records which direction the magnetic north is at that moment in time. So as we began to study the ocean floor using magnetometers, we could start to map out the ocean floor in which direction the magnetic field north was during the time of that rock's formation. We originally believed that it would be just this random pattern, but in reality, this is what we get to see. So when we look at the magnetic record recorded in the basaltic rocks of the Atlantic Ocean, it looks kind of a mess, but what you can see is that those jumbly lines that kind of look messy are all running, for the most part, parallel to the mid-Atlantic ridge. And in fact, if you study these really closely, what you'll find is that there is a symmetry about this, that a band on the eastern part matches up with at the same age and strength as something on the western parts, which implies that these formed from the same time. And when we look at this pattern, what it tells a geologist is it tells us how it formed. What we believe happened is as magma wells up from the ridge, it hardens and records when the rock, where the magnetic poles are. And this process happens over the course of millions and millions of years. But every time it does that, it begins to split apart and separate so that we get this mirror imaging, or the symmetry on the east and the west. All right. That gives us this process of how this striping occurs. All right. The new rocks are being formed at this ridge and then being carried away, very similar to like a conveyor belt, further and further away from the ridge. So again, these magnetic reversals are recorded inside the basaltic rock, and it tells us they're not all the same age. We can see that some are normal and some are reversed. If it was all the same age, we would see that they all had the exact same polarity, and they don't. All right. And the fact that they are symmetrical along those ridges tells us that they formed at the ridges and are moved away. And we can actually match up these patterns to rocks in older lava flows on continents and actually start to put some dates to these things. So what we did when we look at then combining all of this data, we can actually come up with an age of the ocean floor. And here's a map that actually shows the age. Reds are the youngest, blues are the oldest. And you can see exactly as you would expect that if the continents are being spread apart from the crust, from the mid-ocean ridges, right, because that's again where magma is welling up, hardening, and then being dragged away from it, you would expect these to be the youngest. They're also where you find the youngest sediment, the thinnest sediment layers. And the oldest ones are along the edges of the continents, where you have the thickest sediments. We used to think that the ocean floor would be some of the oldest rocks in existence. And in fact, there's some of the youngest. The oldest ones we can find along the continental margins are close to 180 million years old, which is about the right time when Wegener proposed that the continents were drifting apart, roughly 200 million years ago. So the oldest rocks are formed again along the continental margins, way far away from the ocean's mid-ocean ridges. That's where you find the youngest rocks. So let's tie all that together in a theory. A scientist by the name of Harry Hess in the 1960s developed this idea of seafloor spreading, that new ocean crust is being formed at these ocean ridges. And when that magma rises up to the surface at these points of these ridges, it pushes the rock that was previously there away from it. So it's spreading from those mid-ocean ridges. And then at the trenches, that's where the rock is then being recycled. All right? It is being pushed down deep into the Earth's interior to be destroyed. This is the missing link that Wegener couldn't describe. The continents are not plowing through the ocean crust. They're actually being pushed apart from this ocean crust that's being created and driven away from those ridges. So it's kind of floating along on top of the mantle, like a person in a lazy river would be a way that you want to describe it. Not plowing through like a snowplow, but someone floating along a lazy river. This is, again, that missing link that Wegener would struggle with. So what we're going to do then in the following video is take seafloor spreading, combine it with continental drift, and come up with a coherent theory called plate tectonics that truly shows what's happening inside the Earth to cause the plates to move around.